So many gases are actually a mixture of gas or a solution of gases, so made up of many different compounds. And even though it's a mixture, you can treat them as one substance, and then you can determine the total moles of gas in the air. So even though they're made up of different things. So the air that we breathe is 78% nitrogen, 21% oxygen, about 1% argon, and a very small amount of carbon dioxide. And Dalton's law states that the total pressure of all of the gases is equal to the sum of each of those partial pressures. And according to kinetic molecular theory, gases have negligible size and they're not interacting. So they're not going to even notice each other. Also, according to kinetic molecular theory, the average kinetic energy is related to the temperature. So even though particles might have different masses, they're going to have the same kinetic energy, so they're going to have the same total pressure. The partial pressure is the pressure of a single gas in the mixture. And when we add up the partial pressures of each of the components, then it should equal the total pressure from all the gases. If I happen to know the volume and temperature, as well as the pressure, I can find the number of moles, or if I know the volume, temperature, and moles of a gas, I can find its partial pressure. Like I said, the sum of the partial pressures equals the total. So if I know the total pressure, I can say it's equal to pressure of component A plus B plus C, and so on, because the gases are behaving independently. They're not going to be interacting. And this is Dalton's law of partial pressures. So the pressure of any gas is equal to the moles of the gas times RT divided by the volume. So assuming that each of the gases are acting independently, I can find the partial pressure of each gas by multiplying the moles of each gas type. So then I have the pressure of A equals the moles of A times RT over V, the pressure of B equals moles of B times RT over V, and so on. And then if I take Dalton's law into account, I can plug in for each of these partial pressures. I could plug in these equations up here. Notice that RT over V can pull out the side. So basically I get the sum of all the moles times RT over V is equal to the total pressure. And that means that my total pressure is equal to my total moles over RT over V. So we get back out the ideal gas law. If I take the ratio of the partial pressure of a single type of gas over the total pressure, that ends up being the moles of that single component times RT over V divided by the total moles times RT over V. Notice RT over V's cancel out, so I get moles of A over total moles. This is called the mole fraction. So mole fraction is kind of what it sounds like, the fraction of a component over the total. So and it's given by the symbol chi here. The maximum amount of value for mole fraction is 1 if we had a pure substance, so it'll generally be less than 1. And it's the same thing as if we were getting a percentage, but we don't need to multiply by 100. So the partial pressure is equal to, if I know the pressure of A is going to be equal to the mole fraction of A, so basically what percentage of A we have, times by the total pressure. So that will be an equation you'll need to know. So if I have a gas that is, so I know that nitrogen is 78% of the air that we breathe, so find its partial pressure. So I'll find pressure of nitrogen is equal to the mole fraction, so that will be 0.78. I'll take that percent and multiply or divide by 100, times by the pressure of air. So at sea level, it's 1 atmosphere. So that means that the partial pressure of nitrogen at sea level is 0.78 atmospheres. And if I wanted to find out the partial pressure of the other gases, I will just take those percentages, make them fractions, and multiply by 1 atmosphere. And if I added those all up, they should equal the total pressure of 1 atmosphere. So If I have a 1 liter mixture of helium, neon, and argon, so helium, neon, and argon has a total pressure of 762 millimeters of mercury. At 298 Kelvin, if the partial pressure of helium, so helium is 341 millimeters of mercury, neon is a 112, and then it says what's the mass of argon present. So there's a couple different ways that we can go about this. We could either find the partial pressure of that or use the amount total to find the moles of each one. I'm going to find the mole fraction of, or the pressure of argon. So I'm going to do the total pressure, 662, minus each of those other components. And that gives me a partial pressure of argon being equal to 209 millimeters of mercury. So now that I know the pressure of argon, I know the volume and temperature, and I know R, so I can find moles of argon. Oops. So now I can do PV equals nRT. I know pressure, volume, R and T, so I'm going to divide by RT to get moles by itself. So moles of argon is going to be equal to the pressure of argon, 209 millimeters of mercury. Actually, we need to get that in atmospheres. So I'm going to divide by 760. And that gives me a pressure of 0.275 atm. Okay, so I'll plug that in, 275 atmospheres. My volume is 1 liter, it's the right units. The arc constant and temperature, 298 Kelvin. So my moles of argon equals 0.01125 moles. And then I can find the mass by multiplying by its molar mass, which is 39.95 grams per mole. So my mass of argon is 0.449. Oops. 449 grams. So I have a 12.5 liter scuba tank, so volume. And it has helium and oxygen mixture that has 24.2 grams of helium and 4.32 grams of oxygen. And the temperature is 298 Kelvin. Calculate the mole fraction and partial pressure of each, and then the total pressure. So let's convert these grams into moles using their molar masses. I'm going to 6.05 moles of helium, and here use O2, 32 grams per mole, gives me 0.135 moles of oxygen. Okay, so if I want to find the mole fraction of helium, I'm going to do the moles of helium divided by total moles, which is helium plus oxygen. Okay, and that would give me a mole fraction. It's mostly helium, so I should have a decent amount, which is 0.97817 moles of helium. Nope, actually, sorry, no units here. Oops. So I will just say equals mole fraction of helium. So mole fraction is unitless. Mole fraction of oxygen will technically, since it's just those two, will just be 1 minus that. But for the sake of doing the calculation, I will do. Okay, so we'll put moles of oxygen up top. divided by my total moles. So my mole fraction of oxygen ends up being 0.021827. Okay, and those add up to 1, so that's good. Now, you can either find the pressure total by adding up our total moles and then using R, T, and V, or we can do partial pressures of each one and then add up those. So I'm going to actually find the total pressure, but you could do either way. You'll get the same answer. The total pressure is going to be equal to the total moles, times R T over V. So my total moles are my moles of helium plus oxygen, and then R, 0.821 times the temperature, 298 Kelvin, divided by my volume, which is 12.5 liters. So my total pressure is equal to 12.099 atmospheres. Now to find the partial pressure, again, I can do ideal gas law and use the pressures of each of the gases, or I can do my mole fraction. So I can say pressure of helium equals mole fraction of helium times the pressure total, which would be 0.97817 times 12.099 atmospheres, which gives me a pressure of 11.8 atmospheres. The pressure of oxygen is equal to the mole fraction of oxygen times total pressure, so 0.021827 times 12.099. And that gives me a partial pressure for oxygen of 0.264 atmospheres. And then those should both add up to the total pressure, which they do. I'm going to solve these, so feel free to press pause, and then in about 10 seconds the answers will show up and you can, I'll go over them. Okay, so let's break down this first problem. I have hydrogen gas mixed with water vapor. This happens a lot when we do experiments where we're collecting vapor over water. Some of the water vapor gets put into the total sample. So the mixture has a total vapor of 755 torr, and water vapor has a partial pressure of 25. What amount of hydrogen gas is contained in this volume at this temperature? So I know the total pressure and the water pressure, so I can find the hydrogen pressure by subtracting the two. And then I converted those to atmospheres, so I'm in the right units. Now I know that the the amount of moles of hydrogen will be equal to the pressure of hydrogen times the volume over RT. So I can solve for the amount of moles using the ideal gas law, but using specifically the partial pressure. Here I have a diver breathing in the heliox mixture with a mole fraction of 0.05 for oxygen. What's the total pressure if the partial pressure of oxygen is 0.21 atmospheres? So I use this partial pressure equation, which says that the mole fraction times the total pressure is equal to the partial pressure. So I can solve for total pressure here, and when I do that I get total pressure of 4.2 atmospheres. Okay, so like we did in that last problem, a lot of times when we do an experiment, we'll have a reaction happening, gas gets released, and then it gets collected in a little beaker here where we can measure that volume of gas. But because it's going through water, then we're going to have some water vapor involved in there. So if we want to know the pressure of the vapor we're considering, we need to get rid of the water vapor, which is the vapor pressure of water. Okay, So there's a table that you can look up that will tell you the pressure of water, the vapor pressure of water versus the temperature. So for example, if I have a gas collected over water at 25, then I would go look and say, oh, well, the vapor pressure from water is 23.78, so that's how much I'm going to have to subtract from my total pressure. So let's look at this problem. I want to find the rate of photosynthesis. So oxygen gas is emitted in that process, and it's collected over water at a temperature of 293. So that's 20 degrees Celsius at a total pressure of 755.2. So we'll put that there. Millimeters of mercury. Over a specific time period, a total of 1.02 liters of gas, so volume, is collected. What's the mass of oxygen gas in grams? So, and I know the temperature, 293 Kelvin, and I'll put 20 degrees Celsius. That will help us to look up in the table. So if I go back to that table, I know that at 20 degrees Celsius, water, the pressure of water, is equal to 17.55 millimeters of mercury. So if I want to know the pressure of oxygen, that's going to be the total pressure minus the pressure of the water. So that'll be 755.2 minus 17.55 millimeters of mercury, which gives me 737.65 millimeters of mercury. So I can convert that into atmospheres by dividing by 760. So my pressure of oxygen is equal to 0.97059 atmospheres. So to find the amount of moles of oxygen, well, I'll use PV, pressure of oxygen, times V equals moles of oxygen times RT. So to define the moles, I'm going to divide by RT. So my moles of oxygen are going to equal pressure of oxygen times my volume divided by R divided by T in Kelvin. So I get my moles of oxygen equals to 4.118 moles. And I can convert that to grams using the molar mass, 32 grams per mole. So my total mass is 1.32 grams of oxygen got collected. Okay, another example is we have hydrogen gas by reacting zinc and hydrochloric acid. The HCl produces H2 gas, which is collected over water. Suppose a student carries out this reaction and collects a total of 154 milliliters, so volume. So I'm just going to convert that to the liters by dividing by 1,000. And a pressure, total pressure, equals 742 millimeters of mercury and a temperature of 25 degrees Celsius, which is equal to 298 Kelvin. So what's the mass of hydrogen gas in milligrams that the student collects? So we're going to find the pressure of the hydrogen gas by subtracting the pressure, the total pressure, by the pressure of water at 25, which is 23.78 millimeters of mercury. So my pressure of hydrogen that I collect is 718.22. So let's just go ahead and convert that into atmospheres. And that gives me 0.945 atmospheres for the partial pressure of hydrogen. So now I can say my moles of hydrogen equals pressure of hydrogen times volume over RT, like we did in the last problem. So 0.945 atmospheres times by that total volume in liters divided by R divided by T in Kelvin. So my moles of hydrogen is 5.96 times 10 to the negative 3. Converting that into milligrams. So I'm going to first go to grams. The molar mass of hydrogen is 2.02 grams per mole divided by, multiplied by 1,000 milligrams in 1 gram. That gives me 11.9 milligrams of hydrogen were collected. We've touched on this a bit, but the most simple model that helps us to describe the behavior of gases is kinetic molecular theory, or KMT. In this theory, we are basically assuming that gases are just a collection of particles that are in constant motion. They are moving all the time. They do not see or feel each other. They are colliding elastically, and there are a lot of empty spaces between the particles. I would say the fifth one is really that the kinetic energy of each of the particles is related to the temperature. So as I increase the temperature, my kinetic energy is going up. But gas particles are not going to be moving all at the same speed, though. We also want to remember that anytime that they strike a surface, they are exhibiting some force, and that force ends up translating into pressure, where the pressure is equal to the force divided by the area. And this theory quantitatively models the ideal gas law. So now we're going to discuss how the temperature and kinetic energies are related. So from physics, we know that the kinetic energy of just a moving particle is 1/2 the mass times the velocity squared. In the cases of gases, we're going to take each particle's velocity, square them, and then average all of those. So that's what this U is this average squared of the velocities. For a gases that are in the same container, they're going to have the same temperature. So they're going to have the same kinetic energy. So we're going to say each of those gases' energy is equal to 1/2 times Avogadro's number times the mass of each of the individual particles, right? So that will give us the total mass times each of the velocities, average of the squared velocities. So this little m here is the atomic mass. So if we take the atomic mass of each of the particles times by Avogadro's number, that gives us the mass in grams. Just FYI, that's where we're getting that. So all elements have different masses. So the way that they can have the same kinetic energy is for them to have different velocities. So remember, kinetic energy will be the same at a given temperature. Their mass and velocities is just equal. So if my mass is low, then I'm going to have a fast velocity. So little molecules move fast. If I have a really heavy mass, a big mass, then my velocity is going to be low. So I'm going to move slower. So that's how this all kind of plays together. So the root mean squared velocity is what we use in chemistry and physics, where we take this value here, we took the the velocities squared, average them, and then square rooted them, that is the root mean square velocity. Its units are meters per second. And then we're going to use that cursive M for molar mass, and that will be in kilograms per mole. It will be in kilograms, so that way we can be in the right energy units for it to cancel out with joules. The overall relationship that we'll get is that the root mean squared velocity is equal to the square root of 3RT over the molar mass, where molar mass is in kilograms per mole, like we said, and R is our energy R, so that's 8.314 joules per mole Kelvin. And for just like an FYI, that's the same energy or same R as we used for the ideal gas law. But remember that this is in liters atmospheres. That's kind of like work. Remember, work equals pressure, negative pressure times change in volume. And if I want to go from work in liters atmospheres into joules, I had to multiply by 101.3 joules in not mole Kelvin, in a liter atmosphere. So that ends up giving me 8.314 joules per mole Kelvin. So again, same one. We just want to make sure that we're in the right energy units here. And that's why we're in kilograms, because a joule involves a kilogram. And then the units will be meters per second. So this is something we'll use to explore the relationship between molar mass and speed, and also temperature. So notice here is molecular velocity, so our speed versus the fraction of those. So if I have a really light molecule like hydrogen, the average speed is higher than something that's heavier like oxygen. Notice also we're going to have a fraction, so total, the number of molecules is going to be the same. So if I have more molecules going faster, then my total height is going to be lower, because my area under that curve has to be the same for hydrogen as nitrogen as water and so on. So when I have something moving slower, the peak is going to be higher, meaning I have more molecules at that average speed than something that's moving a lot faster. It's also related to temperature. So we know that the average kinetic energy is equal to 1/2 Avogadro's number times the mass of each element in atomic mass units times the squared average of the root mean squared velocities. Kinetic energy is also equal to 3/2 RT. That's another way that we can express our kinetic energy. So we can set these two together. So I'll get 1/2. Remember that Avogadro's number times the mass is equal to molar mass, and we'll have it be in kilograms per mole. So I'll have 1/2 the molar mass times the average of the squared velocities equals 3/2 RT. So then if I want to get velocity by itself, I'm going to multiply by 2 and divide by the molar mass. So those cancel out. I get the average of the squared velocities equals 3 RT over molar mass, and then I square root the whole thing, and that equals the root mean squared velocity. So that's how I got that equation on the other side. So as I increase the molar mass, I lower the velocity. That's one way we can look at it. If I increase the temperature, I increase the velocity as well. So as the temperature goes up, they're going to shift towards higher velocities. Again, they're going to spread out because we have the same number of molecules. We're just shifting, so that will lower the the height of the curve. So we'll have, on average, molecules moving faster at higher temperatures, and we'll still have some molecules moving slow or way fast, but this is just the average. And at lower temperatures, we have a higher peak of that average. Okay, so let's calculate the root mean squared velocity of oxygen molecules at 25 degrees Celsius. Remember, the root mean squared velocity is equal to 3RT over the molar mass. So that's going to be equal to square root of 3, 8.314 joules per mole Kelvin. Temperature, 298 Kelvin. Make sure temperature's in Kelvin. And then molar mass. Now oxygen is 32 grams per mole for O2. So that means we need to divide by 1,000 grams in a kilogram. So that will give me 0.032 kilogram per mole. So what that ends up doing is the kilograms cancel out from the joules. The moles will cancel, Kelvin cancels, and what's left from the joules is meters squared per second squared, and then I square root it. So that ends up giving me a velocity of 482 meters per second. Now let's do the root mean squared velocity of a xenon at 25 Celsius. Whoops, so we'll have the same equation. 3RT over M, molar mass. So we'll have same temperature, so 3 times 8.314 times 298 Kelvin divided by the molar mass. Now xenon's mass is 131.29, so I'm going to divide by 1,000 and I'll have 1.13129 kilograms per mole. So solving for that, I get a velocity of 237.9 meters per second. So xenon was quite a bit larger than oxygen, and it shows because it moves slower than oxygen would. Mean free path and diffusion and effusion are a couple more concepts related to kinetic molecular theory. So the mean free path, if we think about what a free path means, it means basically the amount of space before you run into something, and that's exactly what it is. So it's the average amount of distance it takes for a molecule to run into something else. So it's the average distance before a molecule collides into another molecule or a surface. So as we increase our pressure, we're going to have more molecules hitting into the surface, so that means that the mean free path is going to decrease. So if I have lots and lots of molecules, then it's going to be more likely that I hit into things. If I lower the pressure, I have less molecules hitting into the surface, so it's going to be less often that they hit into each other. Diffusion and effusion are very similar in their names. Their concepts are kind of similar. So diffusion is when a gas spreads from high concentration to low concentration. So for example, if I was to spray perfume, then the process of you being able to smell it across the room would be diffusion. So the gas going from a high concentration over to the other side of the room at low concentration. So that's into an open space. When a gas molecule escapes through holes into an area of lower concentration, it says vacuum, but it could be just lower concentration, that is effusion. So you've seen effusion when you have a helium balloon, and then over time it shrinks because the helium molecules are literally going through the holes in the balloon, in the latex. So that's effusion. They're both related to the root mean squared velocity. So when I have gases at the same temperature, the molecules that are moving faster are going to be the ones that have a higher rate of effusion. So rate of effusion is given by Graham's law, which says that the rate of molecule A divided by the rate of molecule B is equal to the square root of the mass of B over the mass of A. And how they got this was they just took the root mean squared velocity for A divided by the root mean squared velocity for B. So let me just show you. So they did 3RT over the molar mass of A divided by square root of 3RT over the molar mass of B. They literally just took the speeds. And notice the 3RT is going to cancel out if you're at the same temperature. So then I have a denominator of a denominator comes up top, and that's where I get the B over the A. So what this shows me is if I have a molecule, let's say A is tiny, so small molecule A, it should be, so A would have a small denominator, right, because it has a low mass here. It should be moving fast, so it should have a faster rate. And B, being a larger molecule, so we have a large number over a small number, that gives us something greater than 1. Then we have a fast over a slow. Again, it's greater than 1. So these all kind of work out to each other. So let's say we have an unknown gas diffuses at a rate that is 0.462 times that of nitrogen gas. So we're going to write rate of unknown divided by rate of N2 equals 0.462. Okay, at the same temperature, calculate the molar mass of the unknown in grams per mole. So that equals square root. The reason why you have to write out this is so you know which order to put the masses. So if I know, they told me the rate of unknown to the rate of nitrogen. So that means that I'm going to have the mass of nitrogen over the mass of my unknown. So I know the mass of nitrogen. It's 28 grams per mole over my unknown. I'll just call it X. That equals 0.462. So to get the unknown, I'm going to square both sides. And then I get so 28 over X equals 0.462 squared. And then I'm going to cross multiply. So I get 28 divided by 0.462 squared equals X. And that, if I plug that in my calculator, I get 131 grams per mole. Okay, find the ratio of effusion rates of hydrogen and krypton gas. So I'm going to do rate of hydrogen over rate of krypton. We know that hydrogen moves a lot faster, so this should be something greater than 0. So I'm going to do square root of mass of krypton divided by the mass of hydrogen. And that equals, I'll plug in those masses. As long as the units are the same, we should be good. 83.8 grams per mole divided by hydrogen 0.202 grams per mole. Square root the answer, you get 6.45. So this means that hydrogen moves 6 times faster than krypton. So now we're going to go back to ideal gas law and think about how we can use it as a tool for chemical reactions. So just like before when we use molar mass to go from grams to moles, and then stoichiometry to go from moles of A to moles of B, now we can use ideal gas law as a way to get to moles. So remember that we have the moles equals PV over RT. So if I know pressure, volume, and temperature, I can find my moles of my reactant. And then if I want to go back into volume, for example, then I would, again, just rearrange volume equals nRT over P. When everything's a gas at STP, we know our molar volume. When in doubt, just plug it back in. And now we could use, if I know pressure, volume, and temperature of a gas, I can get into moles. So I can use ideal gas law just like I could with molar mass. This chemical reaction shows methanol being synthesized with carbon monoxide and hydrogen. With this ratio, says what volume of hydrogen gas, so I want to know volume of H2, at a temperature of 355 Kelvin and a pressure of 700, so no, pressure equals 738 millimeters of mercury, temperature equals 355 Kelvin, and we need to synthesize 35.7 grams methanol. Okay, so first thing I want to do is get this amount into moles. So I'm going to divide by the molar mass of methanol, which is 32.04 grams per mole. And then methanol is in a gas phase, so it could stop here and then go into volume of this, but I'm actually just going to go straight into switch to hydrogen. So I have mole of CH3OH, 2 moles of hydrogen. So I am going to use my stoichiometry. I have a 1 methanol for 2 hydrogen, and that gives me a total number of moles of hydrogen, 2.2284 moles of H2. Not H2O. Okay, H2. So now I know moles, pressure, and temperature. So I can plug into ideal gas law. PV equals nRT. I know temperature, I know R, I know N, I know P. So I can solve for V by dividing by pressure. And so that gives me volume equals moles of hydrogen, 2.2284 moles times gas constant times temperature, 355 Kelvin. Oops. And I'm going to get my pressure into atmospheres. I'm going to divide by 760. And my pressure in atmospheres is 0.97105. So I'll plug that on bottom. And my volume equals 66.9 liters. So again, using stoichiometry and then the ideal gas law equation. Here I have a reaction has 4.85 liters or 4.58 liters of oxygen formed at 745 millimeters mercury and 308 Kelvin. How many grams of silver oxide decomposed? So I have a lot of info for oxygen gas. Then once I find moles of oxygen gas, I can use stoichiometry to get to my solid. So let's see, I have, volume, 4.58 liters. I have pressure, 745 millimeters of mercury. So let's just get that right away into atmospheres. That equals 0.980 ATM. And I have a temperature. It's 308 Kelvin. So I can find moles. So PV equals nRT. Let's find how many moles of oxygen there are. So I'm going to divide by RT. So pressure, 0.980 atmospheres. Volume is 4.58 liters. Gas constant and temperature, 308 Kelvin. That means I have 0.1775 moles of oxygen. So now I can go use my stoichiometry. Moles of oxygen to moles of silver oxide Now I'm going to use my stoichiometric coefficients. 1 oxygen, 2 silver oxide, and now that I'm in moles of silver oxide, I'm going to use molar mass. So silver oxide's mass is 231.74 grams in a mole. So I can find out that 82.3 grams of silver oxide decomposed. So on this additional question, it wants to know what mass is required to form 388 milliliters of oxygen. So I'm now going to go, my volume is 0.388 liters of oxygen. Temperature is 298 Kelvin. Pressure 734 millimeters of mercury. Again, get that straight into atmospheres. That equals 0.966 atmospheres. So now I can find moles again. So moles equals pressure times volume over gas constant times temperature. So I find out my number of moles of oxygen is 0.0153. Again, go into silver oxide, using 1 mole of oxygen for 2 moles of silver oxide, and molar mass 231. So similar steps, but new conditions, and that would be I would need 7.10 grams of silver oxide. So both of these problems involve STP conditions with gas. So with those, we don't, well, one, you could plug into the ideal gas law, keeping in mind that temperature is 273 Kelvin and pressure is 1 atmosphere. But you can also know that volume, molar volume, is 22.4 liters per mole under these conditions. So if I have 1.24 liters of hydrogen gas at STP, how many grams of water will react with it? So I can use 22.4 liters per mole of hydrogen and then get into moles. So I know I have 2 moles of H2 for 2 moles of water, and then I can go into molar mass. So this is kind of this step cuts it short where we don't have to use ideal gas law, although you could, and I support it. And that would be 0.998 grams of water. Here it says how many liters of oxygen are required to form 10 grams of water. So I have 10.5 grams of water. I'm going to get into moles using molar mass. Now I'm in moles of water. I can go to moles of oxygen. So stoichiometric coefficient. So 2 moles of water for every 1 mole of oxygen. And now I could use molar volume. So 22.4 liters per 1 mole. And that gives me 6.53 liters of oxygen. Now, so far we've been considering ideal gases, but many gases do not behave ideal specifically at high pressures and low temperatures. So ideal gases assume that there are no attractions between molecules and that molecules do not take up space when they're in the gas phase. But under these low temperatures and high pressures, these assumptions are not valid. Let's explore why. So, under low pressures, the molar volume of argon is basically identical to an ideal gas. So if you look down below, when we have a really low pressure, argon is lined up with an ideal gas. Ideal gases are red. and argon is green. When we increase the pressure, argon starts to deviate from that. So as the pressure increases, the molar volume is larger than an ideal gas. Well, think about argon. Argon atoms do actually take up space, right? When the pressure is really low, then the space between the argon molecules is larger. When we start to increase the pressure, so looking down here, we increase the pressure, the molecules get closer and closer together, and now they start to actually take up space. So that makes their volume larger than when they were under ideal conditions at low pressures. So any real gas, its molar volume is going to be larger than the ideal gas conditions. We can see that here as well. Ideal gas versus these other gases. Johannes van der Waals modified the gas equation to help consider what happens to gases at high pressures. So since the molecular volume actually starts to matter, then we need to add a little bit of component to take into account for that. So we are going to include a B coefficient to take into account the molecular volume. So the volume component is for B. So normally a volume is equal to nRT over P, but now to correct for that volume, we're going to take that and add the moles times this coefficient B. And so you can look up that table and it will just depend on what the molecule is. So now nRT over P is equal to V minus NB. You'll see in a minute why that matters. So which postulate in KMT breaks down at high pressures? Well, under high pressures, in general, KMT says that molecules don't take up any space, but now their size starts to matter. At low temperatures, the molecules are said to be moving around all the time. At low temperatures, they slow down. So they start to stick together. They start to feel each other's forces, and the collisions start to be inelastic. So we'll see that next. So as we have high temperatures, molecules are able to move very quickly and are able to be ideal. At low temperatures, the pressure of the gas is less than that of an ideal gas, because at low temperatures, gases spend more time interacting with each other and less time colliding with the walls. So the pressure is actually lower than it should be. So here we see at higher temperatures, the xenon molecule or atom is acting like ideal gas. As we cool it down, it starts to deviate. So now our deviation is lower. So in order to account for the intermolecular forces, or I'm not going to say forces, I'll say attractions. We are going to take into account A. So A is the coefficient for attractions. That kind of makes sense. So under ideal conditions, pressure equals nRT over V. Now we'll have it be less than it would be. So we'll have subtract A times N over V. So the moles over the volume squared is how that ends up working out. So now pressure plus A times N over V squared equals nRT over V. So now we can put it all together and we get that pressure plus A N over V squared times V minus NB equals nRT. So a lot more challenging to calculate gas conditions when they are real, But in general, under low pressures, the most important factor is going to be the attractions, intermolecular attractions. And once we get those high pressure conditions, the most important factor is the molecular volume, since they start to matter. We can see ideal gas on the chart here. PV over RT equals 1. That would be 1 mole. When we have low pressures, then intermolecular attractions will really matter. So here's these big gases, or ones that are polar. And when we have high pressures, molecular volume starts to really take into account. So that's where these start to deviate. And talking about real gases is a great way to transition, because as we get into high pressures and low temperatures, that's when gases start to transition into liquids. And so what we'll end up talking about next in the sequence of this course is our liquid phase and the intermolecular attractions that are important for that, and that's really when gases transition into liquids.